welcome to Algorithm Seminar. Today we're very happy to have Deepanshu Vasal to give a talk. Deepanshu is a research scientist in the Department of Electrical and Computer Engineering at Northwestern University. He received his PhD from University of Michigan Ann Arbor in EEE systems in 2016 and was a postdoc at UT Austin. His current research interests are game theory, multi-agent decision-making, and feedback communication. Before that, he received his bachelor degree in electronics and communication engineering from IIT Guwahati in 2009. Let's welcome our speaker.
Thank you. Thank you so much for having me. So today I'm going to talk about master equation of Stackelberg mean field games. And part of it is joint work with Randall Berry. Feel free to interrupt me at any time in the middle, okay? As we all know, game theory is basically a tool to model strategic behavior interactions in the world. So what game theory does is that in our real world, there are a lot of situations where strategic agents interact with each other, either in social networks, people, markets, and so on, or firms. And game theory gives us a way to explain that behavior or predict the outcomes many times, or provide solutions to some real world problems. Such an is a mechanism design. It provides a solution as auctions, to allocate goods when there are multiple selfish agents involved, or in matching markets, and so on. So, but the question that I want to ask in this talk is what happens if the number of strategic users is large, and they interact with each other, where every agent is affected by the other agent in a statistical way. So every agent is not affected by other agent individually. It doesn't matter to me what any other individual is doing, but in some sense, the aggregate behavior of the market, how that is behaving. And there are a lot of applications of this today in the real world. For example, this is a graph of Facebook network. I mean, the rate at which the social media has rapidly grown in past few years is absolutely insane. And now everybody is connected to each other through this very large network. So many times each individual is affected in these networks in this some sort of statistical sense. So this question becomes important, how if each agent is a selfish agent, how it is affected by the other, and is there a way to better understand this kind of system. Same thing happens in Internet of Things, or cyber physical system, where you will have multiple nodes and each node is making some strategic decision on its own. And the question is how to understand their behavior. Or in smart grids, if you have multiple power generation plants such as solar, wind, geothermal, nuclear, and so on, and you have multiple consumers like electric vehicles, smart houses, and so on. And the question is how do you integrate this very complex system of consumers and producers where they have different demands and different supplies, and how all of them can come together where every agent is selfish to provide a better real world efficient solution. Same thing happens in cloud computing. Suppose you want to give a job to a server, and there are multiple servers and multiple agents who want to give jobs to other people. You have these two bipartite kind of system where you have selfish agents on both the sides, and the question is how to allocate resources in the most efficient way. Same thing happens in ride-sharing platforms. So Uber or Lyft, they are constantly interacting with so many people in a city, where each agent is a selfish agent. They want to minimize their cost and time taken, and Uber wants to decide how to price their rides, and so on. Same thing happens in autonomous driving. If you have these multiple cars driving around in the city, each car is interacting with the cars around them in a complex way, and there's this whole complex network of such cars in a city. In blockchains, you have these different miners. Each miner is trying to mine a block, and each miner is strategic. And the question is how can you talk about this whole system where so many selfish agents, selfish miners are trying to interact with each other in a very complex way. Or in drone swarms. So all of these applications that I talked about, many times what happens is that there's a leader involved, one or more leader involved. So let's say the government or Uber or Lyft or any firms involved. And many times these firms have like commitment power. For example, like we have seen these advertisements that first 25 people will get 50% off, next 50% people will get 35% off, and so on. So leaders many times have this like commitment power, where they can commit to a policy, and the followers best respond to that. So given this policy, the followers will see what is in their best interest. Same thing happens, for example, in Uber and Lyft. Like Uber and Lyft, they give you like a price, and the consumers or the riders decide what kind of price do they want to get, ride they want to get. So the question again is like, what kind of policy should the leader commit to in such cases, knowing that the followers will best respond to it, and how they can maximize their own profit. One example comes in like Google Maps. So in Google Maps, suppose that Google knows like the traffic pattern of the whole city. If it does, how can it reveal the information to the agents? If the Google reveals that some road doesn't have traffic, all people might want to go there. So it might increase traffic there. So what is the most efficient way to reveal this information to the players, such that, let's say, it maximizes the social welfare? So the Google has this objective of social welfare and wants to maximize social welfare. How can I reveal that information to the people? So that's again a commitment policy. For example, in Uber and rides, like you can see like many times you have these dynamic prices or maybe auctions involved at times. So what kind of policies do these leaders want to commit to when they're interacting with these huge markets, such that they can interact in a efficient way? And there are many other systems, like all kind of markets basically, where such kind of distributed decision making is involved. In all of these systems, like the basic ingredients are that there are a large number of some small minor players which are selfish, and there are one or few selfish major players, let's say government or the firms. Each minor player is trying to maximize its expected self-reward. That's a follower, and the leader is trying to commit to a policy such that when the followers best respond to it, it maximizes the leader's expected total self-reward. So both the parties are selfish. The only difference is that the leader has a commitment power. And there are underlying private states of both the followers and the leaders, and they're privately evolving. And in this talk, my goal is to characterize what we call like Stackelberg mean field equilibrium of the game, which means that I'll define more precisely, like what is the equilibrium behavior and how we can characterize it mathematically and how we can find it. So I'm going to go a bit on the math. So Stackelberg mean field games are a good model for such large-scale strategic interactions with the leader. We assume that there are n number of homogeneous selfish followers. So suppose this number of followers goes to infinity, and there's one single leader for now. So I'm only going to consider a single leader, but I'll extend it to the multiple leaders soon. And each follower observe a private type XTFI. So this is the private type of the follower I, and it lies in a finite set. And similarly, the leader also has a private type XLT that also lies in a finite set. And I assume that the types of all the players, the followers and the leaders, basically evolve in this independent fashion. So if I look at the probability on the types given the history, the information history, it basically products out into marginals. And each follower is affected by other follower through a mean field population state ZT. So every follower is not affected by other followers because there are so many of them. You don't care about every other individual. All you care about is some like statistical behavior of the market. That is how each follower is affected. And at the end of each interval T, leader receives an instantaneous reward RL, which is a function of ZT, XL, and AT, and the follower I receives an instantaneous reward that is a function of the mean field state, the leader's state, its own action, and leader's action. So these are like instantaneous rewards of both the leader and the follower. Now I'm going to define like what I call the Stackelberg mean field equilibrium. So in order to do that, I'm going to define three quantities. The first is the best response of the follower. So suppose that the follower knows exactly the mean field trajectory from 1 to capital T, and it also knows the exact strategy of the leader. So sigma L is basically 1 to capital T. So I know the exact dynamic policy of the leader. If the follower knows that, then the follower wants to maximize its reward from time T to capital T for all the information that it has till time T. So from T to capital T, it wants to maximize its reward to go from T to capital T for every history. and it wants to find a policy that maximizes this for all the information and for all times available. So for all of this, it wants to find the best response of the follower as a function of z1 to t and sigma l. Okay. So this, whatever policy is in there, basically maximizes its reward to go for every history. Now, I can also define the evolution of the mean field state if by what is called Fokker-Planck equation. So suppose like the zt plus 1, which is the mean field state, evolves in the following way. So zt plus 1 is a function of zt, the previous mean field, pi t, which are defined soon, the update kernel of the follower, the strategy of the follower, and the strategy of the leader. So if I know these quantities, I can update mean field in a deterministic fashion through what is called Fokker-Planck Kolmogorov equation. And then I also define a best response of the leader. So best response of the leader is defined kind of in a similar way as the best response of the follower, with like one crucial difference. So the leader wants to, if leader has information of z, which means z1 to capital T, then leader wants to find a strategy that maximizes its reward to go from time t to capital T for every information that is available to the leader, and for all time and for all the information. So it wants to find a strategy that maximizes this, knowing that whatever strategy it is maximizing over, the leader is going to best respond to it. So whatever it maximizes over, it chooses the strategy of the follower that best responds to that particular strategy. So I define this best response of the leader in this way, that leader wants to find, for every z, leader wants to find a strategy that maximizes the reward to go for every history, knowing that for everything that it will find and it will commit to, the follower will best respond to it. So knowing that the follower will best respond to it, what policy should it commit to? So using all of this, I can define a tuple sigma tilde f, sigma tilde l, and z as follows. So sigma, all this is a Stackelberg mean field equilibrium in the following way. So sigma tilde f is in the best response of the follower given z and sigma tilde l. Z evolves through a Fokker-Planck equation. And strategy of the leader is in the best response of the leader given z. So if I have like this sigma tilde f, sigma tilde l, and z across time, across players, that satisfy this like coupled fixed point equation that I call as Stackelberg mean field equilibrium. Okay, so now I'm going to talk about like so this is like a huge fixed point equation, like across player, across time, and the complexity of this equation increases double exponentially. So the question is like, how can I compute this equilibrium efficiently? Is there a way for me to compute this equilibrium efficiently? And I want to talk about what is called sequential decomposition. So in this case, sequential decomposition allows us a way to find to compute these equilibria efficiently as follows. So suppose like at any point of time t, the action of the leader. So there is a single agent. Now I'm talking about a different problem. Suppose there is a one agent, and it takes an action at as a function of x1 to xt. So this is the information that is available to the agent at time t, which is x1 to xt, and it takes an action as a function of this information. Now, you assume that the space of the possible strategies increases double exponentially in time, because this information increases exponentially in time. X1 to xt lies in capital X to t, and gt lies in the cardinality of a to the power cardinality of this information. So the gt lies in the space that grows double exponentially in time. So there's no way for me to like efficiently compute this kind of system if it increases double exponentially in time, and there's no hope for me to solve such kind of systems. So in that sense, all dynamical decision problems are interactable if I don't have more structure. But if there is more structure like Markovianity, then I can sequentially decompose this problem, which means AKA the dynamic programming principle to solve this. Which means that I have a backward recursive way to solve such kind of problems. And for MDPs, it reduces the complexity of the problem for double exponential to linear in time. So since a dynamic program, I can go backward recursive, and for each time t, I have to solve an optimization problem. It basically reduces the complexity from double exponential to linear in time. And that's phenomenal. Because like something that I could not solve at all, let's say for time horizon 10, now I can easily solve like 10 is like nothing. Even infinite, like if I were to go to infinite, I can solve something like using if I have this structure. So this is an idea that I want to use in this problem and ask myself like is there a way for me to sequentially decompose this Stackelberg mean field equilibria? And it goes as follows. Suppose I define a common belief like on the leader's state. So let's say pi t of xlt is the probability of xlt given the common information available to all the agents, and that includes the followers and the leader. So this is the probability on xlt given all the information that is available to all the agents. That's a common belief. And I'm going to consider only the Markovian strategies of the leader and the follower as follows. So I'm going to assume that in equilibrium, the policies that I want to compute have the structure that the follower i's action only depends on pi t and zt, which is the common state, and the follower state, which is xf, the private state of the leader at time t. So this is the, like, in some sense, like the current state of the leader. I don't care about the past. So that's why it's Markovian. Similarly, I can define the leader strategy as a function of pi t and zt and xlt, where xlt is the private state of the leader. And again, this is like in some sense the Markovian state. So this is the Markovian strategies. So I'm going to only find equilibria that are Markovian, but I'm going to allow the deviations of the players in general spaces. An equivalent way of finding these strategies as follows. So suppose that here I say that the strategy depends on the common state pi t zt and the private state, but I can correspondingly write it as follows. That suppose the action of the follower at time t depends on is operated through this function gamma, which operates on the private state of the player xt, where this gamma is a function of pi t and zt itself. So I basically break the strategy into two forms. One, I operate pi t zt to get gamma, and then I use this gamma on xf to generate the action. So this is just a different way of writing the strategy. And I can do the same thing for the leader. So first I can use it on pi t zt to generate gamma L. And then once I have gamma L, I operate it on XL to find the action here. So again, a different way of writing this. So if I have this, I can easily show that there exists a function f, basically the Bayes rule, that updates the belief of the common belief. So pi t plus 1 can be easily updated from the previous state using this Bayes rule, where pi t plus 1 depends on pi t, gamma lt, and at. Okay. Now I think I have like all the math or all the framework I need to give you the algorithm. But before I go there, just to make sure, are there any questions? Any questions? No. Okay. Cool. So I'm going to define like a two-step algorithms, like to compute the Stackelberg mean field equilibria as follows. So the first part has a backward way, and the second part has a forward way. So in the backward way, for each for capital time t plus 1, I first define the reward to go functions of both the leader and the follower at 0. This is kind of the standard dynamic program. And then in a backward way, I'm going to define a temporal best response function of the follower as follows. So for every like common state pi t and zt, and for every partial strategy of the leader gamma L, I define a best response of the follower at time t as follows. So for each time t, the follower maximizes its reward to go. So this is the reward to go of the player over its strategy gamma L f, which I put it in red. So it puts a measure on AF and the update of xft plus 1, the state of the follower. So it maximizes its reward to go, where this is the current reward and this is the future reward. And the future reward has two components. This is the update of the pi, and this is the update of the mean field. Both are common states. And in these updates, I'm assuming gamma L, which is like known to me. So I'm like doing it for every like strategy of the leader. So I'm fixing the strategy of the leader, and I'm finding this best response. And then I'm in the update of the mean field, I'm using the solution that I'm seeking itself. So it's like a fixed point equation. So whatever gamma tilde f maximizes this also appears in the update of the mean field. And if I have that, then I can if I solve this fixed point equation for every pi t, zt, and gamma L, that I put it in this best response function and define this best response function to compute this fixed point equation. Is it clear? Like this is just all the fixed points that I'm getting by solving this fixed point equation. I put it in this set. And let me give you like what's the intuition of me solving this. So this says that I want to compute the best response function of one follower. So if the follower knows gamma lt, which is the strategy of the leader, then it wants to maximize its own reward and reward to go knowing that the leader is going to update the mean field, the belief state pi t by this Bayes rule using gamma L, what is given to me, and the mean field will be updated by gamma L and gamma tilde F, which is the other follower. So every other follower is going to play the equilibrium strategy, which is going to update the mean field, and the leader is going to play gamma L, which will update the pi. And knowing this updates, like what any one single follower can do to maximize its reward to go is written here. So it maximizes reward to go over gamma TF. Okay. Now for every pi t zt, I'm going to solve a fixed point equation such that the gamma tilde f is in the best response of gamma tilde L for that pi t zt, and gamma tilde L, which is the equilibrium strategy of the leader, maximizes leader's reward to go. So this is the expected reward to go of the leader. This is the current state, this is the future, where it maximizes over gamma L. So gamma L puts the measure on AL and XL t plus 1 and here. But again, it fixes, like, the update gamma in the update of pi and update of z as gamma tilde. So this is like a weird new fixed point equation that I'm solving, like, for gamma L and gamma F together. So if I solve this like fixed point equation together for gamma F and gamma tilde L, basically I put it in this function theta for pi t and zt. And I call this an equilibrium generating function. And these are my equilibrium policies of temporal equilibrium policies for those players. So I computed for every pi t and zt. And then I plug this back in to compute the value functions at time t of the follower and the leader. So this is like a standard thing what you do for dynamic program, that you first compute your best responses and then plug it back in to compute the value function at time t. So I go backward recursively like this. So this generates basically a function theta for me. For every pi t zt, I compute the equilibrium gamma tilde L and gamma tilde F by solving this temporal fixed point equation, and I compute this theta function. Now, using this theta function, I'm going to generate the strategies as follows. So at time I go forward. So initially, I have my initial common belief on the state of the leader as this, as QL. And then as I go down, I generate my strategy of the follower and the leader as follows. So this follower strategy basically is this theta that I computed. I operated on a pi t and zt. So whatever theta and z I'm hitting, like going forward, I operate my theta function on that, and to find my policies of the leader. And then I update my pi t and zt using the Bayes rule and the Fokker-Planck equation as I go down. So this basically generates like my policies as I go down. I use a theta function on pi t and zt and update my pi t and zt by using the update functions that I have. And this basically defines my policies, and I show basically that this sigma tilde that I just found is a Stackelberg mean field equilibrium, which means that no follower wants to unilaterally deviate at any point of time. So for any history, no follower wants to unilaterally deviate. And similarly, no user wants to unilaterally deviate, which means that if from equilibrium any user deviates to sigma L, knowing that the follower will best respond to it, then no leader wants to do that. So this is an equilibrium for leader also, and together we show that the z that we are getting is updated through the Fokker-Planck equation. So this basically shows that whatever I've computed so far is the Stackelberg mean field equilibrium. So I want to show here more that there's a converse to it also. We show that every Stackelberg mean field equilibrium can be found using this. So we show, suppose there is a Stackelberg mean field equilibrium, sigma tilde L, sigma tilde F, and Z, that is a solution of the fixed point equation. So suppose there exists such a Stackelberg mean field equilibrium. Then I show that there always exists a function theta such that in a backward recursive way, I can solve for the smaller fixed point equation that will give me the bigger equilibrium. So that also kind of answers the question that how can I guarantee that there always exists a solution to this smaller fixed point equation? If there exists a solution to the bigger fixed point equation, which is like, the solution concept, which was solution concept I talked about. If there exists a Stackelberg mean field equilibrium, I can always find it by solving these smaller fixed point equations. So this is what we show. And then like there are a few remarks here that this is like a mechanism design approach. So if the leader is, let's say, social welfare maximizing, then I can assume a particular reward of the leader that maximizes the social welfare of the followers in an expected sense, where I'm taking expectations with respect to z and the mean field. And in some sense, like I can, if I plug that into the system, like the leader is trying to maximize the social welfare. And this could be like, in some sense, Google Maps, let's say. The Google Maps want to maximize the social welfare. It can plug in this function, and it can give you like a mechanism design perspective that if everybody is trying to optimize their own function, how can still Google Maps maximize the social welfare? There are some simpler simplification that if leader doesn't have a private state, then everything kind of simplifies considerably. And this whole algorithm can be easily extended to the infinite horizon case also. So these are few remarks. Next question that I want to get to is how can I extend this to the multiple case? So suppose like now I have multiple leaders. Is there a way for me to extend this whole system to the multiple leaders? And one way I can do that is as follows. That first I define this best response function of the follower in the same way as before. But now I'm assuming that there are n leaders. So in gamma L means that it's a vector of gamma Li for every leader I. So with this vector, I define this best response function for every gamma this vector. So again, I solve the same fixed point equation for the followers. And then every leader solves a fixed point equation as follows. So every leader wants to maximize its reward to go. Where again, like in the update of the belief and the mean field, I put gamma tilde L. And then the follower wants to, follower is best responding to this equilibrium gamma L. So whatever gamma tilde L that I'm seeking from the leaders, the follower is best responding to it, and that basically solves this like temporal fixed point equation, gives me gamma tilde L and gamma tilde F, where this is the vector of all the leaders, and that I plug it back in theta, and then again like in a forward way, I'll define the strategies of the leader and the follower in a very similar sense. So again, like I have this like similar kind of framework kind of goes through when I have multiple leaders as well. Where multiple leaders, like in some sense, like say Lyft and Uber are competing against each other. So they want to find the policies that each of them can commit to while being in equilibrium with the other person, knowing that everybody else, like the minor players, will best respond to their strategy. Now, another extension one can do is what happens when the number of leaders is infinite. This was like finite number of leaders. If the number of leaders is infinite, I can still take the mean field of the leaders. So this is suppose like the mean field state of the leaders that tells me the histogram of the types of the leaders at time t. And again, this mean field again has a similar Fokker-Planck kind of equation for this problem for the leaders. And then I can again solve like a coupled fixed point equation both for the follower and leader as follows. So the follower will have a best response that will maximize its reward to go. This is the reward to go of the follower. Again, solve a very similar fixed point equation for every gamma L. And then the gamma tilde L is like a similar best response fixed point equation for the leader for all the leaders together in some sense. So it maximizes the gamma L. Which puts a measure on AL and here XLT plus 1, where it solves this fixed point equation in gamma tilde L. That is also the solution that I'm seeking. So if I solve this fixed point equation for every time t, it gives me that solution where I have infinite number of leaders, infinite number of followers interacting together in a market where the leaders have a commitment power. So this kind of like gives me puts like the whole meat of the talk that this is like the backward recursive algorithmic way that I'm giving to solve these kind of systems. Okay, so I have an infection. I'll take some examples like to show like how I can use this. So suppose I have a vaccination problem in a society with negative externality. That suppose there are a bunch of cyber physical nodes or people like in the system where each player can be healthy or infected. Healthy, 1 means infected, and each node can take an action 0,1, where 0 means do nothing and 1 means repair. And the dynamics evolve as follows: that this is the healthy state, and you can if you take the repair action, you will become healthy. But if you don't do anything, you will remain in the same state, which could be either healthy or bad, or you could update it. You could get infected by a certain rate. Wi is like a binary random variable with the rate with which you can get infected, and this rate basically kind of is directly proportional to how many other people are infected in the whole society. So if there are more people infected in the society, there are higher chance that each individual will get infected if you don't do anything. And then there's a reward for the follower that this says that the reward of the follower is as follows. You pay a cost if you are infected. So if you are infected, you don't want to be infected, so you pay a cost. And then you also pay a cost to repair yourself. So this is the cost that you pay to repair yourself. And then there's a leader which wants to maximize the social welfare. So it wants that the whole society becomes healthy, but it also doesn't, it might give some, like, let's say, subsidy. It also wants to minimize the subsidy. So this is the subsidy that it gives. The cost that players pay minus, let's say, the actual cost of the vaccine or the repair action. So it wants to maximize this reward and minimize the cost. And we plug this in, and we see like this kind of like equilibrium strategies of the players that we're getting, where this is the cost of the vaccine. So we show that when the fraction of the healthy population is like close to zero, so it means that everybody is infected, then you can still put some cost to the vaccine, because you know that if everybody is infected, everybody has like a natural drive to pay for the vaccine. So you don't have to subsidize much. If nobody is infected, everybody is healthy. Like there's not much infection in the system anyway that a lot of people are getting infected. So you don't have to it doesn't cost like we are in a good enough state. But this is like where you want to give the maximum push. So you want to like give the maximum subsidy here, where the fraction of the population is somewhere like in the middle. So and these are like the utility functions that we are getting. Another example that one can think of is like technology adoption. So suppose there's a game where a firm decides the price of the product, whose utility depends on the preference of the person, but is also directly proportional to how many other people are using that product. So think of like Apple versus Android. Everybody has a preference whether you want to buy Apple or Android, and this is the preference minus 1 or 1, Apple or Android. And they choose an action whether they want to buy one of these products, and these preferences of the buyers evolve independently. So I won't go into the questions. I'll just tell you what it means. So it means that suppose like I am an Android user, I will try to stick to the Android because like there's some sort of like stickiness in the market that whatever I'm buying, I want to stick to that. Unless it so happens that suddenly for some reason, like in equilibrium, like I want to buy Apple. And if it happens, then my preferences might change to Apple. So I might stick to Apple more. So if whatever I'm sticking to, I want to stick to more, unless I buy something else, and then my preferences changes to that, or my stickiness changes to that. And this is the reward that I'm getting. So if I buy the product that I prefer, I get higher reward. But I also get a higher reward if more people are buying that product. So like if everybody is kind of buying Android, it has good ecosystem, it has a lot of like apps, I might want to buy that also. So my reward depends on that. And there's a cost of this product, like Apple or Android. So it's think of it in the following way, that Apple already existed, this cost is exogenous, and Android wants to get into the market, knowing that this is how the dynamics of the market are. So how should it cost like its product? Knowing that this is how the market works, how should it cost it to capture the market in some sense? So if that is the case, so there's only one leader which wants to maximize its revenue. And so again, like we put this in the system, and we get like the equilibrium strategies and the utilities of the players, and how the leader should cost its product. I don't have a lot of intuition on these, but like I mean the whole point was to show that again this is like a very relevant problem that one can easily solve using this kind of system. Okay, so with this I would to conclude and say that I considered like these kind of games where I have one or multiple leaders and an infinite number of followers, with the leaders and the follower each has a private state that evolves in a control Markov process. And as I present a novel dynamic programming like methodology to sequentially decompose this problem of computing this Stackelberg mean field equilibria. And this is what is called as equivalent of Master's equation for Stackelberg mean field games. So again, like an actual question is like I have this like very nice framework now which I can solve, which I could not before because of the double exponential complexity. Now there's so many applications that one can think of. How can I use this kind of framework in all these applications that I can think of to provide better solutions? And one I think very interesting topic is like so all these fixed point equations that I've given temporal are in some sense POMDP kind of fixed point equations and belief states. So one can ask a question like, so instead of optimization, I have a fixed point equation. So one can ask a question, is there like a machine learning, deep learning kind of numerical approaches to solve these kind of systems to provide real world solutions? So like if I take a real market or any of the applications that anyone is interested in, where you have like these leader follower settings, how can I use these machine learning techniques to solve this, use these probability kind of things? And just to put things in perspective, there are numerical methods to solve mean field games. So in mean field games, like, have not a Stackelberg, but normal mean field games where the type space are of the order of r to the power 400. So each type has like lives in this huge space, and there are numerical methods to solve these kind of systems. So that kind of asks a natural question, like, how can one can extend these results to the Stackelberg sense, where there is a firm which can commit to, and how what to do about it. There are some like more academic questions, when this is unique, when it exists, and so on, and how one can extend this to Stackelberg graph on mean field games with both multiple and single and multiple leaders. So with this, I would like to conclude my talk, and I will be happy to take any questions.